Tonight, we're going to talk about one of the most unsettling mysteries unfolding in modern astronomy. In August 2025, using the James Webb Space Telescope, astronomers turned their instruments toward our nearest sun-like neighbor, just 4.3 light-years away. They were searching for a world that, if real, would be the closest gas giant to Earth ever discovered. And for a moment, they found it. A planet roughly the mass of Saturn, orbiting the star next door. But then, something impossible happened. The planet vanished. Follow-up observations found nothing where it should have been. Later observations flickered with signals no known object should produce. The detection refused to settle into a yes or a no. By the end of tonight, you're going to understand how a Saturn-mass world could appear and disappear in the data of our most powerful telescope. Why this triple star system, 3 suns bound together just 4.3 light-years away, sits at the very edge of what we can see, and what this unresolved flicker tells us about how science actually works at the limits of detection, and why this particular star system may be the most important destination in the human imagination. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. That star is called Alpha Centauri. The name has a weight to it. 4 syllables, and suddenly the universe feels both vast and somehow reachable. It sits just over 4.3 light-years from our sun. On cosmic scales, that is essentially next door. Every other star in the sky is orders of magnitude farther away. This particular point of light, is the closest star system humanity has ever known. From the southern hemisphere, Alpha Centauri is one of the brightest objects in the night sky. You can find it without a telescope, without a chart. You look up and there it is, steady and luminous, outshining almost everything around it. To the naked eye, it appears as a single star. One point, one source, but here's where it gets strange. It is not one star. It is 3, gravitationally bound, orbiting together for billions of years. 3 separate suns share this address in space. Alpha Centauri A is the largest of them, slightly more massive than our sun, slightly brighter. Alpha Centauri B is smaller and dimmer, carrying roughly 85% of the sun's mass. Together, A and B trace an elliptical path around each other. At their closest, they come within about 11 AU of each other. That is 11 times the distance between Earth and the Sun, roughly the distance from our Sun to Saturn. At their farthest, they pull apart to about 36 AU, near the edge of our own solar system's classical boundaries. They swing toward each other and away again over a period of roughly 80 years, locked in a gravitational dance that has been repeating since before our own sun was born. And then there is the third star, Proxima Centauri. The name means the closest, and that is exactly what it is. Right now, Proxima sits slightly closer to Earth than A and B do. But the way it fits into this system is nothing like you would expect. Proxima is a small red dwarf, the dimmest of the 3 by a wide margin, and it orbits the AB pair at an enormous remove. Not from across a room, but from across a continent. Proxima sits roughly 13,000 AU from the A and B pair. To put that in perspective, if A and B were 2 people standing in the same city block, Proxima would be a person standing in another city hundreds of miles away, loosely bound by the same gravitational thread. It is part of this system in the technical sense. It completes an orbit around the AB pair, but it takes hundreds of thousands of years to do so. So when we say Alpha Centauri, we mean something more complicated than a single name suggests. We mean a triple system. 3 stars, 3 different sizes, 3 different brightnesses, 1 shared gravitational history. For this story, the focus is one of them, Alpha Centauri A, the largest, the brightest, the one most similar to our own sun. Now, think about what proximity actually means when we start talking about interstellar travel. Right now, every interstellar probe humanity has ever launched is moving at roughly 1,18,000th of the speed of light. At that pace, reaching Alpha Centauri would take roughly 75,000 years. But theoretical designs for future probes, the kind that use laser sails or nuclear propulsion, could reach speeds around 1% of the speed of light. At 1% of light speed, you are moving at about 6,700 miles per second. A beam of light crosses the United States in roughly 0.015 seconds. At 1% of that speed, a probe would cross the same distance in about 1.5 seconds. Still staggering. Still almost incomprehensible, but calculable. At that speed, a probe reaches Alpha Centauri in approximately 430 years. Not a single lifetime, several lifetimes, but finite. An actual number you can write down, plan around, inherit across generations. Compare that to any other target. Barnard's star sits about 6 light years away. At the same 1% of light speed, the journey becomes roughly 600 years. Wolf 359 is 7.8 light years out. That adds another century and a half on top of Barnard's star. Every additional light year is not a small rounding error. It is decades, sometimes centuries. The difference between reachable within a few generations and barely within a civilization's planning horizon. Alpha Centauri is simply the closest possible destination. That fact alone makes it the natural first target for any serious interstellar mission ever conceived. But proximity is not enough. Proximity tells you where to point. It does not tell you whether the journey is worth making. Before any civilization commits resources to a 430-year mission, it needs to know what is waiting at the other end. A probe that travels across 4 light years and arrives to find empty space around a barren star has accomplished very little. The question of what is actually there, what orbits those stars, what kinds of worlds, if any, have formed in those planetary systems, is not a secondary concern. It is the whole foundation of the decision. And that question has been harder to answer than anyone expected. Does Alpha Centauri have planets? For decades, that question sat unanswered. The system was close enough to study, close enough to generate real hope, but the search kept running into the limits of the instruments doing the searching. Small planets around nearby stars are extraordinarily difficult to detect. They are drowned out by the light of the stars they orbit. They leave signals in the data so faint that noise and signal blur together into something barely distinguishable. Here's what scientists believed at the time those searches began. If any star system were going to yield a planet detection, Alpha Centauri was the best candidate. The proximity alone meant the signals, faint as they were, would be stronger here than anywhere else. Decades of searching produced candidates, hints, possible detections that evaporated under scrutiny. And then, a few years ago, one of those hints became something more. A detection that looked, for a moment, like the answer everyone had been waiting for. What happened next would not resolve the question. It would complicate it in ways no one had predicted. So how do we even begin to look? That question sounds simple. It is not. Finding a planet orbiting another star is one of the hardest things astronomy asks us to do. Planets produce no light of their own. They don't shine. They don't broadcast their position. They sit in the shadow of their stars, tiny and dark, and the stars beside them blaze with a ferocity that makes the planets all but invisible from any meaningful distance. The problem is not that we lack the desire to find them. The problem is that everything about the physics of the situation works against us. Think about what you're actually trying to see. A planet the size of Earth next to a star like our Sun is roughly 1,000,000 times fainter. A gas giant is perhaps 10,000 times fainter. Now add the glare. From where we stand, the planet and the star occupy almost the same point in the sky. The star's light washes out in every direction around it. Trying to spot a planet next to its star is like trying to spot a firefly hovering next to a searchlight. Not a dim searchlight. A searchlight visible from miles away. The firefly simply disappears into the wash of light. And yet we have found thousands of exoplanets. Planets orbiting stars across the galaxy. Some hundreds of light years away. Some thousands. We have done this through cleverness. We found ways to avoid looking for the planet directly and instead let the planet betray itself through what it does to its star. The first great method is the transit method. A planet orbiting its star will, if the geometry is right, pass directly between us and the star. When it does, it blocks a tiny fraction of the star's light. The star dims slightly, briefly, and then returns to full brightness. Do this again and again on a predictable schedule, and the pattern is unmistakable. A planet is there. The Kepler Space Telescope found thousands of planets this way, staring patiently at fields of stars and cataloguing every flicker. But the transit method requires something specific. It requires alignment. The planet's orbital plane must line up almost exactly with our line of sight to the star. Tilt the orbit even slightly, and the planet never crosses in front of the star from our vantage point. We see nothing. The planet is there, and we see nothing. Alpha Centauri does not give us that alignment, not for any planet we currently have reason to expect. The geometry simply does not cooperate. The transit method goes quiet. The second great method is radial velocity. This one is more subtle. When a planet orbits a star, the planet's gravity pulls on the star, gently. The star doesn't sit still. It wobbles, slightly, rhythmically, in response to the planet tugging on it. That wobble shifts the star's light toward us and away from us in a repeating cycle. We can measure that shift precisely. It is called a Doppler shift. Blue when the star moves toward us, red when it moves away. From that wobble, we can infer the planet's mass and its orbital period. This method has worked brilliantly for stars that stand alone. Single stars with clean, steady light signals where the wobble from a planet stands out against the background noise. Alpha Centauri is not a single star. Alpha Centauri A and Alpha Centauri B are orbiting each other. Two stars, tugging on each other through a mutual gravitational dance that takes roughly 80 years to complete one full cycle. That orbital motion produces enormous Doppler shifts in both stars. Enormous compared to any signal a planet would produce. The radial velocity data for Alpha Centauri A and B is dominated by this binary interaction, a constant gravitational conversation between two stars that completely overwhelms the faint whisper a planet would add to the data. Wait, think about what that means. We have a star system 4 light years away, closer than anything else, producing signals strong enough to detect. And the system's own architecture is burying those signals under noise we cannot separate from the thing we are looking for. The nearest stellar neighbor in the sky is, by a particular and frustrating irony, among the hardest systems in the galaxy to search for planets using the methods that have worked everywhere else. 2 of the 3 standard approaches are effectively closed to us. The transit method fails on geometry. The radial velocity method fails on architecture. That leaves the third method, direct imaging. And direct imaging is, in its own way, the hardest of all 3. Direct imaging means what it says. You point a telescope at a star, and you try to photograph the planet itself. You try to catch the reflected light of a planet, or the faint thermal glow the planet radiates from its own warmth against the overwhelming brightness of the star right next to it. The firefly and searchlight problem, directly confronted. The only way to do it is to make the searchlight disappear. Astronomers have built instruments called coronagraphs to do exactly that. A coronagraph blocks the star's light before it reaches the detector. Think of holding up your hand to block the sun on a bright day. Suddenly, the landscape around the sun becomes visible. Things you could not see through the glare come into view. A coronagraph does this precisely and mechanically. blocking just the star's light, while allowing the surrounding region of sky to be observed. But even with a coronagraph, the challenge is enormous. Stars do not disappear cleanly. Light diffracts around the edges of the blocking element. Scattered light bleeds into the field. The residual glow is still many times brighter than any planet nearby. You need an instrument that is extraordinarily sensitive, extraordinarily stable, and extraordinarily cold. Heat produces infrared noise. Even tiny thermal fluctuations in the telescope itself can drown out the faint signal from a distant planet. In December 2021, a telescope launched that changed what was possible: the James Webb Space Telescope. JWST was designed to see the universe in infrared light, the long wavelength glow of heat rather than visible light. This matters for planet hunting in a specific way. Planets are warm. Even planets far from their stars retain heat from their formation, from radioactive decay inside their cores, from the slow cooling of whatever material compressed and collided to make them. That residual heat glows in infrared. In visible light, a planet next to its star is billions of times fainter than the star. In infrared, that ratio improves. Not enough to make it easy, but enough to make it possible. JWST is also cold. Extraordinarily cold. It operates in deep space, shielded from the sun by a tennis court-sized sun shield that keeps its detectors at around minus 233 degrees Celsius, only 40 degrees above absolute zero. At that temperature, the telescope's own thermal noise drops to nearly nothing. The faintest infrared signals from the distant universe, including the warmth of planets, can be detected without being buried in the detector's own heat. And JWST carries coronagraphs, multiple coronagraphs, designed to block stellar light with precision that previous instruments could not match. Here is where Alpha Centauri's proximity becomes an asset rather than a complication. Direct imaging struggles most with planets that orbit close to their stars, because from our vantage point, those planets sit almost on top of the stellar disk, practically touching the glare. The farther a planet sits from its star in actual space, the wider the angle between them appears to us. And because Alpha Centauri is so close, any planet there would appear at a wider angular separation from its star than an identical planet orbiting a star 10 times farther away. The proximity that makes Alpha Centauri the obvious target for interstellar travel also makes it one of the better candidates for direct imaging. The stars are close enough that a planet in the habitable zone, or beyond it, would appear to sit at a distance from the stellar glare where JWST's coronagraph could actually work. We had a telescope now capable of doing what no previous instrument could do. We had a nearby star system where the geometry favored the attempt. The combination was not something anyone was going to leave unexplored. And what the first attempt found was not what anyone had predicted. In early 2025, a team of astronomers did exactly that. They submitted a proposal to use JWST not on some distant galaxy, not on a nebula hundreds of light years away, but on the nearest star to our own sun, Alpha Centauri A, the bright, sunlike candidate, the one whose architecture had defeated every previous method. The observations took place over several weeks in late spring and early summer of 2025. JWST pointed at Alpha Centauri A, engaged its coronagraph to block the star's direct light, and turned its infrared cameras toward the faint space around it. The goal was simple to state: find something that should not be there. A faint point of light, orbiting in the dark. But pointing a telescope at a star and finding a planet are two completely different problems. The first is engineering. The second is science. And between those two things sits one of the hardest challenges in modern astronomy. How do you know when what you are seeing is real? Think about what the cameras are actually recording. Every exposure captures millions of photons. Most of them do not come from a planet. They come from the star itself, leaking around the coronagraph. No coronagraph is perfect. Light diffracts around the edges of the blocking mask. Scattered light bounces off the telescope's optics. The infrared detectors pick up thermal noise. The result is a glowing halo of residual starlight surrounding the mast center. A planet, if it is there at all, would be a faint point embedded inside that halo. Trying to find it directly in a single image is nearly impossible, and Alpha Centauri A makes this problem worse than usual. The star is one of the brightest objects in the southern sky. Even with the coronagraph, the scattered light background around it is significant. This is not a faint star the team was pointing at. It is an extraordinarily bright one. The residual glow after masking had to be carefully modeled, calculated, and subtracted from the raw data before anything faint could be searched for at all. This is where the rotation strategy becomes the foundation of the entire method. The team did not take one long exposure and call it an observation. They took multiple images, each one with the telescope rotated to a slightly different orientation. A few degrees between each exposure, then they compared the images. Here is why that matters. A real planet orbits the star. It has a fixed position relative to Alpha Centauri A. When you rotate the telescope, the planet's position in the image shifts by exactly the amount you would expect from the rotation. It stays where the star says it should be, but instrumental artifacts work differently. The internal reflections, the detector imperfections, the optical ghosts that appear when an extremely bright star floods the camera. These stay fixed relative to the telescope itself. When the telescope rotates, the artifacts rotate with it. The planet moves as the star does. The artifacts move as the telescope does. Think of it like trying to look at something through a window. There is a smudge on the glass. When you tilt your head, the smudge moves with the window. But whatever is outside the window stays where it is. The rotation strategy turns that distinction into a test. Rotate the telescope. If the candidate moves correctly with the star's frame of reference, it is real. If it rotates with the telescope, it is an artifact, not a discovery, a reflection. That test alone is not enough. A point of light that passes the rotation test could still be a background star, a distant galaxy, or something else entirely. This is where multi-wavelength imaging comes in. Planets are not neutral objects. Their brightness at different infrared wavelengths depends on their temperature and their atmospheric composition. A warm gas giant absorbs and emits differently than a cold, rocky world. The spectral fingerprint, the pattern of brightness across different wavelengths, tells you something about the physical nature of the object you are looking at. The team imaged Alpha Centauri A across multiple infrared bands. Any candidate that turned up would have to match the profile of a real planet. Not just appear in the right place, actually look like what a planet should look like. Each observation session ran for several hours. This is not unusual for JWST. The telescope was designed for long, patient exposures on faint targets, but keeping the coronagraph effective over hours of observation requires something remarkable from the telescope's guidance system. The star has to stay centered on the blocking mask to within a fraction of an arcsecond. An arcsecond is 1/3600th of a single degree, a fraction of that. If the star drifts off the mask even slightly, its light floods the detector and overwhelms everything else. JWST's fine guidance system makes this possible. It monitors the star's position continuously and makes corrections thousands of times per second. Thousands, not once a minute, not once a second. Thousands of times each second. The result is a telescope that holds its aim with a precision that has no real comparison in everyday experience. It is stability at a scale that requires engineering most people will never encounter. Each session produced gigabytes of raw data. Images carrying the infrared signatures of everything JWST's cameras could detect. From the star's residual halo to the faint thermal glow of space itself. That data was transmitted to Earth by radio waves, received at ground stations, and fed into a calibration pipeline. The pipeline corrected for detector sensitivity variations, optical distortions, and background noise. The subtle imperfections that every instrument carries and that every precision measurement must account for. What came out the other end was not a clean picture of a planet. It was a processed dataset. A map of infrared brightness around Alpha Centauri A, with known artifacts removed, calibrated against the telescope's own characteristics, and ready for scientific analysis. The signal, if there was one, would not announce itself. It would have to be found. The point of all this is not the technology for its own sake. It is what the technology makes possible. The rotation strategy eliminates false signals from the telescope. The multi-wavelength imaging provides physical confirmation. The pointing precision keeps the coronagraph working over hours of observation. The calibration pipeline removes the instrument's fingerprints from the data. Each layer of rigor is a layer of defense against misidentification. Against the mistake that has haunted planet searches around Alpha Centauri before. The moment when something appeared to be a discovery and turned out not to be. The observation design itself is where the scientific weight lives. Any claim that emerges from this data would carry the full force of every correction, every calibration, every comparison across orientations and wavelengths. The method had been built so that a real signal, if it existed, could be trusted. The data was collected. The processing was done. What the analysis found next would test everything that framework was built to protect. What came out of that work was a faint point of light. Not a streak across the detector. Not a smear of scattered glow. A point. Small, faint. Sitting in the darkness around Alpha Centauri A at a distance of roughly 400 million miles from the star. That is about 2.7 times the distance from our Sun to Earth. Close enough to be in the inner system. Far enough to be outside the worst of the stellar glare. The team had a signal. The question was whether the signal was real. This is where science becomes something almost methodical in its caution. A faint point of light in infrared data is not a planet. It is a candidate. The history of planet searches around Alpha Centauri specifically had shown what happens when candidate becomes announcement too quickly. So the team did not announce. They tested. The first check was straightforward. Did the point appear in multiple independent images taken at different times? Not just once, in a single exposure. Repeatedly, across separate observations. It did. The signal was consistent across multiple looks at the same region of sky. That ruled out a random spike in a single detector read, a cosmic ray hit, a one-time noise event. The signal was stable. The second check cut deeper. When the telescope rotated between exposures, did the point stay fixed relative to Alpha Centauri A? This is the same logic built into the entire observation design. Instrumental artifacts move with the telescope's frame of reference. Real objects in the sky stay anchored to the star. The point stayed anchored. Across every rotation, every shift in the telescope's orientation, the point held its position relative to the star. Not drifting, not shifting, fixed. That ruled out the telescope as the source. The third check looked outward rather than inward. The team searched the star catalogs and deep sky surveys for any known object at that location. A background galaxy, a distant red dwarf, anything that might already be on record. There was nothing. No known source at that position. The point had no prior identity. 3 checks done. The signal was stable, anchored, and unidentified. But there was more. The 4th check examined the light itself. Not just whether a signal existed, but what kind of signal it was. Spectral analysis, meaning the measurement of brightness across multiple infrared wavelengths rather than a single band, showed a pattern consistent with a warm gas giant. A planet of significant mass, glowing with its own internal heat, with an atmosphere that absorbed and re-emitted infrared light in a specific way. The answer was stranger than expected. The spectrum did not just show generic warmth. It showed absorption features consistent with methane and water vapor. Specific molecules, the kind of molecules expected in the upper atmosphere of a gas giant, the same molecular families found in Jupiter and Saturn. The signal was not just bright, it had chemistry. The fifth check settled the most fundamental question of all. Was the object actually part of the Alpha Centauri system, or was it simply in the same direction as seen from Earth? An unrelated background object that happened to appear nearby. To answer this, the team tracked the point's motion through space over time. Stars move. Alpha Centauri A is close enough that its proper motion, its slow drift across the background sky, is measurable across even short-time baselines. If an object is gravitationally bound to Alpha Centauri A, it moves with the star. If it is a background object, it does not. The point moved with the star. It shared Alpha Centauri A's path through space. Gravitationally bound, 5 independent checks, 5 confirmations. The team now had a mass estimate, roughly 95 Earth masses. That is approximately the mass of Saturn, the second largest planet in our own solar system. Not a rocky world, not a super Earth. A gas giant smaller than Jupiter with Saturn as its closest analogue. The temperature estimate came from the infrared brightness, between 500 and 1000 degrees Kelvin. That range needs a moment to sit with, because it is strikingly different from anything in our own solar system. Jupiter's visible cloud tops reach about 125 Kelvin. Saturn's cloud tops sit at roughly 95 Kelvin. Both are intensely cold at the surface, even though their deep interiors reach temperatures of tens of thousands of degrees. The visible layers of our gas giants are frigid. The planet around Alpha Centauri A, if real, was running far hotter than either of them. Why? 2 possibilities and no certain answer. The planet might be young, still radiating the heat left over from its own formation, the way a forge stays hot long after the fire is removed, or it might simply be more massive, with greater internal pressure generating more heat. Both are plausible. The data could not distinguish between them. That question remained open, and the team left it open rather than choosing an answer the evidence did not support. Now comes the number that carries the most weight of all. The detection confidence was 5 sigma. Sigma is the unit statisticians use to describe how far a result sits from what random chance would produce. A 5 sigma result means the probability of the signal being noise, of the point of light being a random fluctuation in the data rather than a real object, is less than 1 in a million. That is not a comfortable margin. It is the same threshold particle physicists required before they would declare the discovery of the Higgs boson, the particle predicted by theory for decades, and finally confirmed in 2012. Not a loose standard. Not a cautious estimate. The hardest confirmation bar in modern experimental science, and this signal cleared it. Not marginally, cleanly. Every check passed. The signal was stable across multiple images. It was anchored to the star's reference frame. It had no known catalog source. Its spectrum matched a warm gas giant with methane and water vapor in its atmosphere. It moved through space with Alpha Centauri A. Its mass and temperature were physically plausible for a young or moderately massive Saturn-class world. And the statistical confidence reached the same threshold used to confirm one of the most sought-after particles in the history of physics. The team's conclusion was careful. Everything the data could test, the signal passed. Every property a real gas giant should have, this object had. For a moment, the closest star system to our own appeared to harbour a world. But the signal had only been asked the questions the team could think to ask. There was a question none of them had anticipated. And when it arrived, it would change the picture entirely. So the question shifts. Not what does the data say, but what does it mean? What is this thing, actually, if it is real? Think about Saturn. Most people picture the rings first. That sweeping halo of ice and rock, glowing faintly in the outer solar system. But beneath the rings is a planet on a scale that is difficult to hold in the mind. Saturn is the second largest planet in our solar system, a sphere of hydrogen and helium so massive it could contain dozens of Earths. And yet, There is no ground to stand on, no surface where you could set down and look up. If you descended into Saturn, you would pass through layers of thickening gas, the pressure building, the temperature rising. Eventually the gas would stop behaving like a gas. It would become liquid, denser and denser, deeper and deeper, until you reached a region where hydrogen is compressed so completely that it conducts electricity. Metallic hydrogen, a material that does not exist naturally anywhere on Earth. Below that, possibly a rocky or icy core at the center. Though even after decades of study, we are not certain. The exact internal structure of gas giants remains one of the genuinely open questions in planetary science. A Saturn-mass planet at Alpha Centauri A would almost certainly be similar. Hydrogen and helium. No solid surface, rings probably, moons almost certainly. And that last word matters more than it might seem. Saturn has over 80 confirmed moons. 80. They range from captured rocks barely a kilometer across to massive spherical worlds with geologies of their own. And 2 of them in particular would make any astronomer pause. Titan is larger than the planet Mercury. It has a thick nitrogen atmosphere, the same dominant gas as Earth's air, but the surface pressure on Titan is roughly 50% higher than the pressure at sea level on Earth, and the temperature sits around 94 degrees above absolute zero. That is roughly minus 179 degrees Celsius. At that temperature, water ice is not soft or slippery. It is as hard as granite. It is bedrock. But methane is not a gas on Titan. Methane is a liquid. It fills lakes, it carves river channels, it collects into seas near the poles. Titan has a complete liquid cycle the way Earth has a water cycle, but the liquid is not water. It is hydrocarbon. Orange clouds made of organic haze hang in the sky. The sun from Titan's surface is a dim smudge through the murk. It is an alien world with familiar processes running on entirely different chemistry. And then there is Enceladus. Enceladus is much smaller. A moon you could cross in a few hundred kilometers. But beneath its smooth, icy crust is a liquid ocean. Not frozen, not a slush. A real subsurface ocean of liquid water, kept warm by tidal forces generated by Saturn's gravity. At the South Pole, geysers crack through the ice and spray that water into space. Not just water, ice particles, organic molecules, the chemistry of life's building blocks erupting from a frozen moon into the vacuum of space. Some of that material falls back to the surface. Some of it feeds one of Saturn's rings. And scientists looking at that plume see something that makes them lean forward. Liquid water, organic molecules, and a heat source. Those 3 things together are the conditions that produce life on Earth. Enceladus has all 3. Now imagine that the Alpha Centauri A planet is real, and imagine it is truly Saturn-like. If it has 80 moons, or even a handful of larger ones, some of those moons might be Titan-like. Some might be Enceladus-like. The planet itself may not be the interesting object. The interesting objects might be circling it, quietly, in the dark. But the implications do not stop at the planet's moons. In August 2025, the team submitted their findings to a major astronomy journal. They did not wait for the peer review process to complete before making the announcement public. That pattern, submitting a preprint and issuing a press release before formal publication, has become increasingly common in modern science. The reasoning is straightforward. Results this significant should reach the community immediately. Other teams need to begin follow-up work. Every week of delay is a week of lost observation time. The news moved fast. Within days, headlines were running worldwide. Planet found around Alpha Centauri, gas giant orbiting our nearest stellar neighbor. For most people alive on Earth, it was the first time Alpha Centauri had registered as anything more than a name in a science book. Now it had a world. Something else was happening. The planet itself was not the most consequential implication of the discovery. Gas giants do not form alone. That is one of the firmer conclusions from planetary science. The conditions that produce a massive hydrogen and helium world, the disk of material around a young star, the accretion processes, the gravitational architecture that settles over millions of years. Those same conditions typically produce smaller planets too. Rocky ones, planets with surfaces, planets closer to the star, where temperatures are warmer. Alpha Centauri A has a habitable zone. The band of distances where a rocky planet with liquid water on its surface is physically possible. That zone runs from roughly 0.7 to 1.3 astronomical units from the star, approximately the range from Venus to Mars in our own solar system. If Alpha Centauri A had already produced a gas giant at 2.7 AU, the same disk that built that giant likely left rocky material in the inner system. Some of it may have assembled into planets. Some of those planets may sit inside that habitable zone right now. Any one of them could have an atmosphere, could have oceans, could have had billions of years to develop whatever chemistry arises in warm, wet, sunlit places. Space agencies began discussing what a mission to Alpha Centauri might actually look like. Not as a thought experiment, as a scheduling question. The Breakthrough Starshot project, first proposed in 2016, had already laid out one vision. Tiny probes, barely the size of a postage stamp, propelled by laser arrays from Earth to 20% of the speed of light. At that speed, the 4 light-year crossing takes roughly 20 years. The probes would not stop. They would fly through the Alpha Centauri system and transmit data back across the void. But 20 years is a human lifetime, not a civilization's. People alive today could wait for that signal to arrive. For a few weeks in the late summer of 2025, that felt less like a proposal and more like a timeline. Alpha Centauri had transformed. Not a distant curiosity, not a point of light used to calibrate telescopes, not a system that had defeated every previous attempt to find its planets. A destination, a place where something was waiting. The question was whether that something was actually there. 2 months passed. The world had spent late summer with Alpha Centauri transformed in its imagination. Space agencies drafting timelines, probe concepts pulled from drawers and dusted off. The nearest star system reframed overnight as a place where something was waiting. And then, quietly, a second team of astronomers filed a request with the James Webb Space Telescope Scheduling Office. They wanted to follow up. Same star, same instruments, same techniques. They simply wanted to look again. In October 2025, they did. The star was there. Alpha Centauri A, burning steadily in the infrared. Bright as always, exactly where it should be. They ran the same rotation strategy, the same multi-wavelength comparisons, the same calibration pipeline. They checked the entire field around the star. The planet was gone. Where the signal should have appeared, there was nothing. No faint infrared point of light. No spectral fingerprint. No trace of the object that had cleared 5 independent confirmation checks 2 months before. The team checked their data reduction. They checked their calibrations. They checked for systematic errors in the observation design. They went through the entire field source by source. The star was normal. The detectors were functioning. The data was clean. Nothing. In November 2025, they published their non-detection paper. The language was careful. They did not accuse the original team of error. They did not claim the original signal had been fabricated or misidentified. They simply reported what they had done, step by step, and what they had found. Or rather, what they had not found. The paper's conclusion was precise and unsparing. Using the same instruments and the same methods, at the same star, the planet was not present in the data. The astronomy community did not receive this quietly. Within days, the discussion had spread beyond journal servers and conference threads. Social media filled with arguments. The astronomy subreddit ran dozens of parallel threads, each dissecting a different corner of the problem. Popular astronomy bloggers published analyses. YouTube astronomers recorded responses. The debate was not chaotic exactly. It was something more uncomfortable than chaos. It was careful people looking at the same situation and being unable to agree on what it meant. because the situation itself made no physical sense. The question that kept surfacing in every forum and every comment thread was the same one. How does a Saturn-mass planet disappear? Let's sit with what that question actually implies. The detected object carried a mass of roughly 95 Earth masses. That figure is almost impossible to hold in the mind. But think about what it means physically. An object with that much mass is held spherical by its own gravity. It has enough material to pull hydrogen into metallic states deep in its interior. It generates its own internal heat through gravitational compression. This is not a pebble. This is not a cloud of gas that might drift apart or scatter. This is a structured, gravitationally bound world. Such a thing cannot simply cease to exist between one observation and the next. The picture did not hold. The most obvious way a planet could vanish is destruction. Some catastrophic event removes it from the picture, and what remains scatters across the surrounding space. That scenario has a problem. A very large problem. Destruction leaves traces. Destruction does not produce silence. Consider what catastrophic destruction actually looks like. Roughly 4.5 billion years ago, in the early history of our solar system, an object roughly the size of Mars struck the young Earth. We call that impactor Theia. The collision vaporized rock. It melted the outer layers of the Earth. It threw an enormous mass of material into orbit. Material that eventually coalesced into the Moon. The Moon is not a coincidence. It is the visible, still present aftermath of that impact. Billions of years later, the evidence is still there, hanging in the sky every night. That was a Mars-sized object hitting a rocky planet. What happens when a gas giant with a mass roughly 30 times larger than Mars experiences a catastrophic collision? The energy involved is not comparable, it is staggeringly greater. The heating alone would be comparable to fusion-level temperatures at the collision point. The debris cloud produced would be vast and hot and bright in the infrared. Astronomers would see it for decades, possibly centuries afterward. The field around Alpha Centauri A would not be quiet. It would be glowing. The October observations showed a quiet star, not a faint glow around the impact zone, not excess infrared at any wavelength, not a diffuse cloud of heated material spreading outward from the planet's last known position. Nothing. Alpha Centauri A appeared utterly unremarkable, a star going about its slow, stable life 4.3 light-years away, giving no indication that anything in its vicinity had changed at all. So the destruction scenario fails, and fails decisively. Not for lack of imagination. Because physics demands evidence and the observations supplied none. What astronomy had on its hands by late November of 2025 was not a dispute between two teams with different views on technique. It was something more fundamental. The original detection had been rigorous. It had cleared every testable criterion. It had met the same statistical confidence threshold used to confirm the Higgs boson. And 2 months later, the planet was simply not there. Both things appeared to be true at once. And they could not both be true. The question was not going away. How does a massive planet appear and then disappear? And if it did neither, if it was never really there, or if it was still there and somehow invisible, then what had each team actually seen? The answer, when it began to take shape, would not come from looking harder at either observation. It would come from looking more carefully at something almost everyone had overlooked. So the two results sit there, irreconcilable, and the question they raise is not going to resolve itself by staring at the data again. What it demands, instead, is something different. A step back. A willingness to consider the simplest stories first, before reaching for anything complicated. Start with the most ordinary explanations, the ones that don't ask us to invoke anything strange. See how they fare. The first and most parsimonious explanation is this. The original detection was a false positive. The team saw an artifact, a background object, a systematic error in the data and mistook it for a planet. The planet never existed. It wasn't there to disappear. This is not a reckless suggestion. False positives have a long and instructive history in astronomy. In the 1960s, a radio telescope in Cambridge picked up a signal so regular, so precise, so unlike anything natural, that the astronomers running the project half-seriously nicknamed it LGM-1, Little Green Men. The signal pulsed on and off with a period so exact it could have been a broadcast. It turned out to be a rapidly rotating neutron star, a pulsar, sweeping its beam of radio energy across space like a lighthouse, perfectly natural, perfectly periodic, perfectly surprising. The exoplanet field has its own version of this. In the 1980s and into the early 1990s, several research teams announced planet detections using the radial velocity method. The star wobbled. The wobble implied a companion. The companion had mass. The math was there. But on closer inspection, most of those early detections fell apart. The wobble was real. The cause was not a planet. It was the star itself, its surface pulsating, its magnetic spots rotating in and out of view, mimicking the gravitational tug of something in orbit. The signals were genuine. The interpretation was wrong. Those false starts reshaped the field. The community spent decades building stricter standards. Today, an exoplanet is not considered confirmed until multiple independent teams verify it using different methods or instruments. For direct imaging specifically, the bar is even higher. The object must appear in multiple independent images. It must move with the star through space, gravitationally bound, not drifting past on its own trajectory. It must have planet-like spectral properties, not just a smudge of brightness that might be anything. The Alpha Centauri detection met every one of those criteria. That is the part the false positive story has to account for. The original team had been careful. They checked for artifacts. They ruled out background contamination. They used standard techniques that had successfully found planets before. They reviewed the work internally before submitting, and the detection came in at 5 sigma confidence, a probability of pure statistical noise producing that signal of less than 1 in a million. 5 sigma detections are almost never statistical accidents, but something was wrong. If the detection was a false positive, it was not a statistical one. It would have to be a systematic error, some artifact or contamination that was not properly accounted for. And here is the problem with that. What kind of systematic error produces a point source at exactly the right position, with exactly the right brightness, with spectral features consistent with methane and water vapor, appearing in multiple independent images, taken at different telescope orientations, bound to the star's reference frame, and then simply gone in the follow-up? Not an artifact that wanders or smears, not scattered light, which would shift position as the telescope rotates, not a background galaxy, which would not move with Alpha Centauri A across the sky. Not thermal noise from the detector, which would not produce sharp spectral absorption features. Whatever this hypothetical false positive was, it would need to be extraordinarily specific. It would need to pass every test that real planets pass, then fail the most basic test of all. It would need to not be there when someone looked a second time. That is possible. Systematic errors can be subtle and stubborn and invisible until the right analysis exposes them. The community does not dismiss the possibility, but it is not a comfortable explanation. It asks you to believe that an artifact behaved, in every testable respect, like a real planet, and then stopped. The second explanation is gentler, more forgiving of both teams. The planet is real. The planet was always real. But during the follow-up observations, it was behind Alpha Centauri A from our perspective, hidden not by destruction, not by error, but by simple geometry. This is called occultation. It happens all the time in our own solar system. Venus passes through what astronomers call superior conjunction, roughly every 19 months. That is the point in its orbit where it travels behind the Sun from Earth's point of view. When that happens, Venus is still there. It is still moving, still massive, still real. We just cannot see it because the sun is in the way. Mars has superior conjunctions too. When Mars passes behind the sun, mission controllers stop sending commands to surface rovers because the sun's corona interferes with the radio signals. The planet disappears from communication for weeks, then reappears, unchanged. Could the Alpha Centauri planet have done the same thing? The math is specific, so it is worth walking through. The planet's original position placed it roughly 400 million miles from Alpha Centauri A. Johannes Kepler's third law tells us that the square of a planet's orbital period is proportional to the cube of its average distance from its star. For a star similar to the Sun, a planet sitting at 2.7 AU takes roughly 3 to 4 years to complete one full orbit. In 3 to 4 years, that planet traces a circumference of approximately 1,700 million miles. The two JWST observations were separated by about 2 months. 2 months is roughly 1/18 of a 3 to 4 year orbital period. 1/18 of a full orbit is about 20 degrees of motion around the star. 20 degrees is not very much. Picture a clock face. 20 degrees is the difference between the 12 and the 1. For the planet to move behind its star in 20 degrees of orbital motion, the orbit would need to be pointed almost directly at us, nearly edge-on, like a spinning coin viewed from the side rather than from above. Orbits are not born preferentially edge-on. They orient randomly in space. The probability that any given orbit happens to be nearly edge-on to our line of sight is a few percent. Not zero, not impossible, but not likely either. And even granting an elliptical orbit, where the planet moves faster at some points and slower at others, the math still requires near-perfect alignment. Kepler's second law, which describes how orbital speed varies, does not offer enough flexibility to make the occultation work without the geometry already being almost exactly right. So the occultation explanation is not ruled out. A few percent probability is not zero. But it accumulates coincidences. The orbit would need to be tilted just so. The planet would need to be at exactly the right phase during the follow-up. The original observations would have needed to catch it at a different phase, one where it was visible. Stack those requirements on top of each other, and what seemed like a simple, natural explanation becomes a story with an uncomfortable number of moving parts. Not impossible, increasingly contrived. 2 ordinary explanations. The first dissolves when you ask what kind of artifact could pass every confirmation test, and then vanish. The second dissolves when you walk through the orbital geometry and count the coincidences it requires. Both of them started as simple stories. Neither of them stayed simple. The simplest stories had failed. The ones that remained were stranger. And the strangest of them all was still ahead. So the strangest stories remained. And the strangest of them invited a question that most people, confronted with a missing planet, would be willing to entertain for at least a moment. Maybe the simple explanations failed because something simple did not happen. Maybe something violent did. Let's consider that possibility seriously. Planetary collisions are not science fiction. They are part of the history of every solar system we have studied closely, including our own. Our moon exists because of one. Roughly 4.5 billion years ago, a Mars-sized body, now called Theia, struck the early Earth. The collision vaporized rock, melted the outer layers of our planet, and threw enough material into orbit to eventually coalesce into the moon. The moon is still there. Every time you look up at it, you are looking at the aftermath of a catastrophe that happened before complex life existed anywhere on this planet. Mercury may carry a different kind of scar. The leading hypothesis is that a large impactor stripped away most of its original outer layers, leaving behind a world that is disproportionately dense and metallic, a remnant of something much larger. Uranus tells the same story from a different angle. It rotates on its side, tilted 98 degrees from its orbital plane. Something hit it, something enormous hit it, and the planet has been rolling through the solar system at that angle ever since. A permanent record of a collision that nobody witnessed. These events were real, but they all have something in common. They happened billions of years ago, in the chaotic early period when planets were still migrating, orbits were still shifting, and the solar system had not yet settled. Computer simulations of planetary system formation show the same pattern every time. Protoplanets form, interact, collide, merge, scatter. It is violent and unpredictable. But after roughly 1 billion years, the violence tapers off. The survivors occupy stable orbits. The dangerous early period is over. Alpha Centauri A is approximately the age of our Sun, between 4.8 and 6 billion years old. Its planetary system, if it has one, would have passed through that chaotic early period and reached stability somewhere between 3 and 4 billion years ago. It has been settled for a very long time. In a system that old, in a planetary architecture that's settled, major planet-to-planet collisions are extraordinarily rare. The rate is roughly once per billion years, and that estimate may be generous for a system with a stable, orbital structure. Now, consider the specific timing required by this hypothesis. The first observation was in May 2025. The follow-up was in October 2025. The collision would have had to happen in that 2-month window. The probability of a major collision occurring in any specific 2-month period in a mature planetary system is approximately 1 in 6 billion. Not lottery odds. Worse than lottery odds. Dramatically worse. But the probability alone is not what rules the hypothesis out. Even in an extraordinarily unlikely event, probability can be wrong. What rules it out is the aftermath. A collision between two gas giants would not be quiet. Gas giants are composed almost entirely of hydrogen and helium, held in layered states by immense gravitational pressure. When two objects of that mass collide, the impact energy is staggering. The atmospheres compress and heat violently. Fusion-like events are possible at the collision point. The material does not disappear. It expands outward. Gas, dust, fragments of whatever rocky or icy cores existed. A glowing infrared cloud forms, and it does not cool quickly. Expanding and cooling takes years to decades, not months. In the first weeks and months after the collision, that debris cloud would be one of the brightest infrared sources in the entire system. JWST, which is specifically designed to detect faint infrared signals, would not miss it. It could not miss it. The October observations showed none of that. No debris, no excess infrared at any wavelength. No diffuse heated material spreading outward from the planet's last known position. Alpha Centauri A appeared unremarkable. A normal star, a quiet system, a destroyed gas giant should be blazingly visible for years after the event. This system looked like nothing had happened. The dramatic explanation, the science fiction flavored story, collapses under its own requirements. Not a near miss, a complete failure. The evidence that should have been overwhelming was simply absent, which left the quieter possibility. Maybe the planet was not destroyed. Maybe it was still there, and the second observation simply failed to see it. This is a different hypothesis from the false positive story. The false positive assumes the original detection was an error. This one assumes the original detection was real, and that the failure belonged to the follow-up. Two honest observations, but one of them missed something. Several ways that could happen. Start with the most technically specific. The coronagraph at the heart of JWST's planet detection capability requires extraordinary alignment to function correctly. The mask must be positioned to a precision of a few milliarcseconds. That is a few thousandths of an arcsecond, which is itself a tiny fraction of a single degree. Think of trying to hold a needle steady above a candle flame, not moving it by more than the width of a human hair, while the entire structure supporting it vibrates slightly with every thermal fluctuation. That is the level of control required. JWST's fine guidance system is designed to achieve and maintain it, but precision systems have tolerances, and tolerances occasionally produce anomalies. If the alignment was even slightly off during the October observations, more starlight would leak past the mask. the background noise would rise. A faint planet hovering near the detection threshold in May could fall below it. There is also the possibility the planet cooled. Young planets lose heat over time. A planet just barely bright enough to detect in May might fall below the detection threshold by October if it dropped even tens of degrees in infrared output. This sounds plausible until you check it against what we know about how gas giants actually cool. Jupiter and Saturn have been cooling for 4.5 billion years. They are still warm. The timescale for meaningful thermal change in a gas giant is not months, it is billions of years. A 10-degree drop in 5 months would be physically inconsistent with how objects of this mass behave. The viewing angle offers another possibility, though a narrow one. Gas giants are not uniform. They have storms, atmospheric bands, complex surface features. Jupiter's brightness changes depending on which hemisphere faces the telescope. When the Great Red Spot is on the visible side, Jupiter is slightly brighter. But this effect is small, typically a few percent. Making a detected planet disappear entirely would require a brightness change of roughly a factor of 10. Atmospheric features do not produce that, not even close. Contamination or instrumental drift are also possible. Cosmic ray impacts accumulate in JWST's detectors over time, creating noise patterns. Optical surfaces can experience gradual contamination from outgassing within the telescope structure. Both are real effects, and both are monitored continuously by the JWST operations team. No major change between May and October was reported. The more subtle possibilities are harder to dismiss entirely. A cosmic ray strike during the specific observation window could corrupt a small region of the detector in ways that obscure a faint signal. A data pipeline bug, one affecting only certain observation configurations, could suppress a real detection without flagging an error. These are not leading candidates, but they are difficult to fully rule out, because they are by nature intermittent, localized, and sometimes invisible in the diagnostic record. What this hypothesis offers is not a clean answer. It offers a set of possible explanations, most of which are too small to account for the disappearance on their own, and a remainder that is genuinely hard to eliminate. The instrumental failure story does not collapse the way the catastrophe story did, but it also does not resolve cleanly. None of the specific failure modes, examined individually, add up to a complete explanation. Two more ordinary stories, one ruled out by physics, one left open but unsatisfying, and the question that neither answered was still waiting, and the answer it pointed toward was stranger than any of the explanations that had already failed. Stay with the possibility that the planet is still there, not destroyed, not hidden behind its star, not the result of an instrument that misfired. Still there, orbiting Alpha Centauri A at roughly the same distance it always was, doing exactly what it was doing when JWST first detected it. The question becomes not what happened to the planet, but what happened to the light. Space between planets is not empty. This sounds obvious, but it is easy to forget. Even in the quietest regions of a mature planetary system, there is gas and dust, remnants of the protoplanetary disk that built the planets in the first place. Far more tenuous than any vacuum a laboratory on Earth could produce, but present, drifting, slowly spreading. Many star systems have debris disks, structured rings of dust and rock, orbiting at various distances from the star, extended versions of what we see in our own solar system. We have several of these structures ourselves. The asteroid belt, sitting between Mars and Jupiter, is a band of rocky material that never assembled into a planet. The Kuiper belt, extending beyond Neptune's orbit, is a vast reservoir of frozen bodies. And closer to home, there is the zodiacal dust cloud, so thin it is nearly invisible, yet real enough to catch sunlight. On a very dark night, far from city lights, you can sometimes see it as a faint pyramid of glow along the horizon before dawn or after dusk. That is the zodiacal light. Sunlight scattering off billions of microscopic dust particles drifting in the inner solar system. We live inside a cloud of debris and barely notice it. Could something similar explain the Alpha Centauri planet's disappearance? If the planet's orbit passes through a denser region of debris around Alpha Centauri A, that dust could absorb and scatter its infrared emissions. The planet would appear dimmer, possibly too dim to detect. As the planet continued its orbit and exited the dense patch, it would reappear, just as it did in May. There is even a smaller scale precedent. In the 1990s, Comet Shoemaker-Levy 9 broke apart and its fragments struck Jupiter across several days. The impacts created dark spots in Jupiter's atmosphere that persisted for months, visible even in amateur telescopes from Earth. Debris, altered chemistry, and changed surface conditions stayed observable long after the collisions ended. External material can change what a planet looks like from a distance. That much is established. The reading came back reversed. JWST sees no strong evidence of a dense debris disk around Alpha Centauri A. This matters. A disk dense enough to hide a Saturn-mass planet would itself emit infrared radiation. Dust absorbs starlight and re-emits it as heat. A ring of material thick enough to obscure a gas giant would glow, and JWST would detect that glow even if it could not resolve individual particles. Whatever disk exists around Alpha Centauri A appears to be sparse, more like our own asteroid belt, which is far too thin to hide anything, than like the dusty disk of a young planetary system. And beyond that, the timing needs to be right. The planet had to be inside a dense patch during the October follow-up, but not during the original May observations. 2 months apart, sitting precisely at the boundary of the patch during the first look, and fully inside it during the second. Possible, but it requires the kind of coincidence that starts to feel like a different problem. The dust explanation does not collapse the way the catastrophe hypothesis did, but it does not come easily either. So set it aside for a moment and consider a different kind of invisibility. Not dust between us and the planet, but something happening inside the planet itself. Gas giants are not the stable, featureless spheres that early illustrations made them appear. They have dynamic, constantly shifting atmospheres, and our own solar system has shown us, repeatedly and in detail, how dramatic those shifts can be. Jupiter's Great Red Spot is the most famous example. A storm system larger than the whole Earth, spinning continuously in Jupiter's southern hemisphere, visible through any decent telescope pointed at the sky. In the 1800s, it spanned roughly 24,150 miles across. Today, it measures closer to 10,000 miles, less than half its historical size, and still shrinking. Its colour has changed too, cycling between deep brick red and pale salmon, depending on conditions that scientists are still working to understand. A feature once considered permanent has been visibly diminishing for over a century. Saturn has its own version. A hexagonal jet stream circles its north pole. Six-sided, roughly 18,600 miles across, larger than our entire planet. Voyager first detected it in the 1980s, and scientists were not quite sure what to make of it. A geometric shape, a persistent atmospheric structure, maintained by dynamics that have no close parallel on Earth. The hexagon has persisted for decades, but it changes too. During Saturn's long winter, when the pole tilts away from the sun for years at a time, the hexagon fades from view. During summer, when sunlight reaches the pole, it returns. Saturn's year is about 30 Earth years long. Each season lasts roughly 7.5 Earth years. The atmospheric reorganization that comes with those seasonal transitions is significant. And then there are Saturn's great white spots. Massive storms that erupt roughly once every Saturnian year, driven by convection from heat rising out of Saturn's interior. Saturn radiates more energy into space than it receives from the Sun. That excess heat builds in the interior and eventually breaks through in explosive convective events. In December 2010, the most recent great white spot erupted in the northern hemisphere. Within weeks, it had grown to encircle the entire planet, visible to amateur observers watching from Earth through backyard telescopes. By mid-2011, it had faded. A storm that wrapped around a world larger than Earth appeared, and then was gone in less than a year. Neptune provides an even more striking case. Voyager 2 observed it in the late 1980s and found a massive oval feature in the southern hemisphere called the Great Dark Spot. Winds around it exceeded 1,040 miles per hour, the fastest winds measured on any planet in the solar system. When the Hubble Space Telescope looked years later, the Great Dark Spot was gone. Not faded, gone. A new dark spot had appeared in the northern hemisphere. Later, it too vanished. Neptune's storms do not linger the way Jupiter's does. They appear and disappear on timescales of months or years, for reasons that are still not fully understood. This matters for the Alpha Centauri question more than it first appears. Textbooks describe gas giants as steady, stable objects, dependable emitters of infrared heat, reliably warm, generating a consistent glow from their long, cooling interiors. That description is not wrong, but it is incomplete. Even within our own solar system, gas giants undergo atmospheric changes that are dramatic enough to alter what they look like from a distance. Neptune's Great Dark Spot did not just shift in color, it vanished from a world we could barely see as a disk from Earth. The idea that a planet could change its appearance significantly is not exotic. We have seen it happen. Now consider what the Alpha Centauri planet's atmosphere might be doing. Gas giant atmospheres are stratified. The deepest observable layers are cloud decks, ammonia ice crystals in the colder upper regions, water ice and other compounds in warmer layers below. Higher up, above the clouds, hazes form through photochemistry. Sunlight breaks apart methane and other organic compounds. The fragments recombine into hydrocarbons. These condense into thin aerosol particles, like a very high, very thin smog layer sitting above the main cloud tops. If haze production in the Alpha Centauri planet's upper atmosphere increased rapidly, that haze could reduce the planet's infrared brightness, not by blocking internal heat from escaping entirely, but by altering what frequencies of infrared reach JWST's detectors and in what quantities. A dramatic enough change could push the planet's apparent brightness below the detection threshold. Not destroyed, not hidden by external dust, just quieter, temporarily, in the wavelengths JWST was looking for. This is more plausible than dust obscuration. It requires no lucky orbital geometry, no dense debris ring, no fortunate timing with an external cloud. The mechanism is intrinsic. The planet itself changes. What it would require is an extreme change, happening in a very short window, weeks, not months. Seasonal changes on Saturn's scale take years to unfold. Whatever happened here, if this explanation is right, happened faster. There are possible triggers. Gas giant seasonality is real. Saturn's axial tilt is 26.7 degrees, close to Earth's 23.5 degrees, and seasonal transitions drive real atmospheric reorganization. A planet in a different orbit around a slightly different star could have a larger axial tilt, faster atmospheric response, or chemistry that reacts more quickly to changes in solar illumination. None of that has been established, but none of it is physically impossible. And there is a third variant of the hidden planet idea, simpler in concept but equally dependent on coincidence. A second object orbiting Alpha Centauri A, smaller and dimmer than the planet, passing between the planet and our line of sight at the moment the follow-up observations were made. A dust clump, a dark companion, an undetected body on a crossing orbit. Some variable stars dim periodically because circumstellar material occasionally crosses our view of them. The same geometry could apply here. From our position, the planet would simply be blocked. This does not require the planet to be destroyed or altered. It requires something else to be in the way. The problem is the same as occultation. The timing has to be precisely right. The blocking object would need to be at exactly the right position, in exactly the right orbit during a 2-month window, and nowhere near the line of sight 2 months earlier. Not impossible, not confirmed, not dismissed. These three possibilities share something important. Each of them leaves the planet intact. Each of them offers a mechanism by which a real object could become temporarily invisible without being destroyed, without having never existed, without a telescope failing in some untraceable way. They are each strange in their own fashion, but none of them asks physics to do something it has never done. Neptune's great dark spot appeared, lasted for years, and then was gone. If a storm on Neptune can vanish, if Saturn can erupt in a planet-encircling tempest and then fall quiet within months, if dust drift through planetary systems, leaving hazes that scatter light in ways we are only beginning to measure, then a planet that was visible in May and absent in October is not necessarily a paradox at all. It might just be a planet having a very unusual few months. The dust remains uncertain. The atmospheric variability remains unconfirmed. The transiting obscura remains speculative. But the question that all three of them point toward is the same. And it is not the question anyone was asking when the original detection was announced. The question is not whether this planet exists. It is whether we understand enough about what gas giants do to know when we are looking at one clearly and when we are looking at a temporary shadow. That question was not in any of the papers, but it was the one the data had quietly been asking all along. Astronomers looked again in late December 2025. The third round of observations began roughly 4 months after the original detection, 2 months after the non-detection that had divided the community. This time, multiple teams had been granted telescope time, including several allocations made under the director's discretionary authority, a special category reserved for urgent, contested science. Different instruments, different wavelengths, different coronagraph configurations, NERCam covering the near-infrared range from roughly 0.c to 5 microns, MIRI reaching further into the mid-infrared, from 5 to 28 microns. The thermal behavior of the telescope itself as it orbited was carefully modeled and accounted for. Every team ran their own analysis. Every team used the same rigorous pipeline the original observers had used. The results came in over several weeks. They were complicated. Some of the December images showed something. A faint point of light, barely above the noise floor, appearing near the position where the planet had been. It appeared in multiple independent images from the same observing session. It moved with the star. It was in roughly the right location, allowing for the orbital motion of an object completing a full circuit over 3 to 4 years. But it was significantly fainter than the original detection. More than half its brightness was gone. A gas giant does not dim by more than half in 4 months. Not by atmospheric variability, not by seasonal change, not by any mechanism anyone had a clean explanation for. That was the first sign that something unusual was happening. But here's where it gets strange. It was not consistently there at all. Within the same observing run, hours or days apart, results contradicted each other. One observation showed a faint hint of something at the expected position. Another observation, taken the same week, showed nothing. Not a dimmer signal. Not a marginal detection at the edge of confidence. Nothing. Different teams analyzing identical raw data reached different conclusions. One group said the signal was real but unusually variable. Another group said the December images showed only noise arranged by chance into a plausible configuration. A third group took a middle position. They could not agree, and they were all looking at the same photons. The January observations using MIRI, the longer wavelength instrument, produced the same pattern. Sometimes a faint source appeared at the expected location. Sometimes nothing appeared. The position was roughly consistent with where an object in a multi-year orbit should have drifted. But the brightness varied in ways that had no precedent. One observation recorded the source at approximately 30% of the original detection's brightness. Another observation 3 days later recorded nothing, with an upper limit below 10% of the original. A third observation a week after that showed something even fainter, and at a slightly offset position. The numbers do not fit any known category. No known physical object varies in brightness this way, flickering on and off in days, by factors of 3 or more, randomly, without a repeating pattern. Astronomers have a long catalogue of objects that vary in brightness, and every one of them has a structure. Cepheid variables are massive pulsating stars that swell and shrink in a regular rhythm, brightening and fading over days to weeks, with changes typically around a factor of 2. Predictable. Clockwork. Nothing like this. Eclipsing binaries dim in a predictable pattern as one body passes in front of another, the same geometry repeating every orbit. Cataclysmic variables involve a star dumping material onto a companion until a nova eruption flares suddenly, and then fades over weeks or months. That pattern is also recognizable, also structured. None of them match what the December and January data showed. Planets do not flicker. They reflect or emit steadily. Atmospheric weather might produce brightness changes of 10 to 20% as different hemispheres rotate into view, as different cloud systems catch the light differently. Not factors of 3, not factors of 10. Not randomly within the same observing week, with no repeating cycle. One more explanation was considered and set aside. What if the original detection was not a planet at all, but a transient event? Something that briefly glowed and then faded. Astronomical transients include supernovae, gamma-ray bursts, and tidal disruption events, which occur when a star is torn apart by a black hole. But a supernova at Alpha Centauri's distance, 4.3 light-years, would be visible to the naked eye, brighter than Venus. The entire night sky would have reacted to it. That did not happen, and the object in the original images did not look like an explosion's afterglow. It looked like a point source moving with the star, spectrally consistent with a warm gas giant. Smaller collisions between asteroids or smaller rocky bodies do not produce glows visible from 4 light-years away for months at a time. The energy is too small. The transient hypothesis does not survive contact with the data. By February 2026, the community had divided into 3 positions that showed no sign of converging. The first was that the original detection had been a false positive, and subsequent observations were finding noise in the same general region of sky, because teams were looking for something, and the human tendency to see pattern in noise is persistent and powerful. The second was that the planet was real, and the inconsistent detections indicated genuinely new physical phenomena. Some previously unknown mechanism by which a gas giant could be temporarily invisible, hidden from a specific wavelength of observation, without being destroyed or displaced. The third position held the middle. Something is at that location, but it is not a simple planet. Perhaps a planetary collision still in progress, a cloud of debris not yet dispersed. Perhaps a planet with an unusual ring system scattering light unpredictably. Perhaps a dusty substellar object with brightness that varies from its own internal processes in ways gas giants in our solar system do not. As of early 2026, none of the 3 positions can be ruled out. No team has definitively explained why the observations behave the way they do. History offers no comfort here, only context. In the 1840s, astronomers announced the existence of Vulcan, a planet orbiting inside Mercury's orbit. Reputable observers claim to have seen it during solar transits and eclipses. Observations followed for decades, mixed and inconsistent. Vulcan was eventually shown not to exist. The sightings were misidentifications, telescope artifacts, and the strong human desire to confirm a prediction. The Alpha Centauri situation may follow that arc. But history also runs the other direction. When Michel Mayor and Didier Queloz detected 51 Pegasi b in 1995, the first planet ever confirmed orbiting a sun-like star, the initial reaction from parts of the community was skepticism. A gas giant completing an orbit in 4 days, inside what should have been a barren zone close to the star, seemed physically impossible under existing formation models. The planet was real. The models needed revision. When the first pulsar signal arrived at Cambridge in 1967, The regularity was so perfect, the team briefly logged it as a possible artificial transmission. It turned out to be a rotating neutron star, a category of object nobody had fully expected to exist in that form. Both times, the universe was doing something real that our frameworks had not anticipated. The Alpha Centauri planet may follow that arc instead. We do not know which one yet. Future observations are already planned for late 2026 into 2027. Using different infrared wavelengths, attempting spectroscopy to break the light into its component colors and study any atmospheric chemistry, and pushing toward optical wavelengths where the background contamination behaves differently, and some systematic errors can be tested independently. 2 future instruments will eventually change what is possible. NASA's planned Habitable Worlds Observatory, currently in early development, is specifically designed for direct imaging of Earth-like planets around nearby stars. Its mirror will be larger than JWST's, and its coronagraph are more capable of suppressing scattered stellar light. The extremely large telescope, being built in Chile, with mirrors between 30 and 40 meters across, is scheduled for completion in the late 2020s. With its adaptive optics systems, it may rival or exceed JWST's sensitivity for some observations, and can study the sky every clear night continuously, not in limited scheduled windows. Resolution will come. It may take years. What we already know about this system is real, confirmed, and not going away. Proxima Centauri, the red dwarf companion orbiting far from the AB pair, has confirmed planets. Proxima b was detected in 2016 at roughly Earth's mass, orbiting in Proxima's habitable zone. Proxima c was tentatively identified through radial velocity measurements, larger and farther out. Proxima d, announced in 2020, appears smaller than Earth. These objects do not vanish when observed. They have been confirmed by multiple independent methods. Proxima is a very different kind of star than Alpha Centauri A, a dim red dwarf versus a sun-like yellow star, and the comparison only goes so far. But the system has confirmed planets. The neighborhood has proven itself capable of forming worlds. Decades of radial velocity work on Alpha Centauri. A itself have ruled out hot Jupiters, massive planets in close orbits like the ones easiest for that method to detect. Any planets around Alpha Centauri A must be either farther from the star or smaller. Computer simulations of gravitational stability in the double star system show that stable orbits around Alpha Centauri A can exist within roughly 3 astronomical units. Beyond that distance, the gravitational pull of Alpha Centauri B, tugging across the star system's internal space, disrupts orbits and makes them unstable over long timescales. The object detected at 2.7 astronomical units sits near the outer edge of that stable zone. If it is real, it is close to the boundary of what the system's architecture can sustain. That boundary matters. If the planet is confirmed real, it tells us that Alpha Centauri A can form gas giants in its outer system. Gas giants at those distances tend to be gravitational shepherds, clearing debris from the inner system and making it easier for smaller rocky planets to settle into stable orbits. A gas giant at 2.7 AU could mean a more orderly inner system, a better chance that rocky planets exist in the habitable zone between 0.7 and 1.3 AU from the star. A gas giant at 2.7 AU could mean moons. The way Saturn's moons populate Saturn's neighborhood, moons with their own heat sources and chemistry. The implications extend outward from the detection in ways that are not trivial. If the planet is a false positive, that also tells us something. Direct imaging at the edge of what current instruments can resolve produces ambiguous data. A 5 sigma detection can still be wrong if the systematic errors are poorly understood. That is not a failure. It is the boundary between what we can currently see and what we cannot yet reach. And knowing exactly where that boundary lies is itself a result. Science moves forward by learning its own limits as precisely as it learns the facts. We are standing at the edge of detection capability. At this margin, different observations can give different answers. Different teams can look at the same data and reach opposite conclusions. That is not a breakdown of science. That is what science looks like at the frontier. Alpha Centauri is not a curiosity anymore. It is a threshold. If planets are confirmed there, they become the first worlds beyond our solar system that humanity might realistically reach, with technology being designed now or that will be designed in the coming decades. In 2026, we stand at that threshold. The question is not whether we will eventually learn what orbits Alpha Centauri A. The question is when and what we will do with the answer. The vanishing planet is a reminder that the universe does not always cooperate with our expectations. That nature is subtle in ways our models have not yet captured. That the most interesting questions are often the hardest to answer, because the universe has no obligation to arrange itself at a scale or a brightness or a stability that our instruments can cleanly resolve. We look anyway. We build better instruments. We look again. A century ago, we did not know other stars had planets at all. 50 years ago, we had no method to detect them. Today, we are arguing genuinely and seriously about whether a specific object at a specific distance from a specific star in the nearest star system to our own is a planet or a shadow. That argument is a form of progress, not the comfortable kind, the real kind. Maybe future telescopes will resolve the flicker into a clear, repeating signal with a physical explanation nobody has yet proposed. Maybe the Habitable Worlds Observatory, years from now, will image not just the gas giant, but a rocky world in the habitable zone, and the whole conversation will shift. Maybe the signal will fade under continued scrutiny, and we will learn it was the instrument all along. Or maybe the ambiguity will persist, and Alpha Centauri will remain both near and mysterious, the closest star system we can see with our own eyes, and the one we understand least. Whatever the answer turns out to be, the search has already changed what we know, and what we know we do not yet know. Somewhere out there, 4.3 light years away in a direction that appears as a bright point in the southern sky, the answer already exists. We are learning slowly and carefully how to read it.